What if the very equations that describe our universe were just broken? What if, when you tried to ask a simple question like, hey, what's the mass of an electron, the math just screamed back at you with an impossible answer: infinity? Well, for a while, this is exactly what happened. It was a crisis that pretty much broke physics. So let's get into it. We're going to be talking about one of the most powerful and, frankly, one of the most controversial ideas in all of physics. It's called renormalization. I know, it sounds a little intimidating, but trust me, it's this beautiful, weird, and wildly successful idea that basically saved physics from itself. So here's the game plan for today. First, we're going to dive into that crisis of infinity. Then we'll see how zooming in on reality gives us a crucial clue. After that, we'll look at the clever sleight of hand physicists came up with. We'll walk through the recipe for how it all works. And finally, we'll ask the big question: what does it all mean? All right, let's set the scene. It's the early 20th century. Quantum mechanics is the hot new thing, right? It's this powerful tool for understanding the tiny subatomic world. But it was hiding this huge, disastrous secret. And when I say embarrassing, I mean it was a complete roadblock. They had these amazing new theories to describe particles and forces, but the second they tried to use them for actual real-world calculations, the whole thing just collapsed. I mean, imagine you're an accountant, and every single time you add up a list of numbers, your calculator just shows infinity. That is literally the problem physicists were facing. Basic fundamental things about our universe were coming out as infinitely large. And we're not talking about a small mistake here, a rounding error. No, the very heart of the theory was just wrong. So what do? What does it even mean when your math keeps spitting out the same single, totally useless result? Infinity. This symbol was haunting them. It meant that a single electron had infinite mass and infinite charge, which is, well, it's obviously nonsense. You can't build a theory of everything if you can't even get the electron right. It's like trying to build a skyscraper on a foundation of quicksand. So how in the world did they fix this? Well, the solution came from a massive shift in how they thought about things. And the answer, surprisingly, wasn't about finding a better calculator. It was about totally rethinking what a particle even is, and realizing that the answer really depends on how closely you're looking. And here is the absolute key insight. The properties of a particle, like its charge, they're not just one fixed number. Turns out they actually change depending on how much energy you use to look at them. What you see, it really depends on your point of view. Okay, think of it like this. It's like a picture on your computer. When you're zoomed out, you see a clear image, right? A simple little point, that's our electron, with a nice, definite mass and charge. At this low energy scale, everything works great. Right, but what happens when you zoom in? In physics, zooming in means hitting something with more and more energy. And as you crank up the power and get closer and closer, that simple, clean picture, it starts to get messy. Because as you zoom way in, that one little electron is revealed to be this buzzing, chaotic storm of virtual particles, these little phantoms of energy just popping in and out of existence all around it. And our original equations, they tried to add up the effects of all of those infinite interactions. And that's the thing that absolutely shattered the math. That's where the infinity came from. So this is where the magic comes in. Physicists came up with a technique to handle all this chaos. It's called renormalization, and it's honestly one of the cleverest and maybe one of the most controversial tricks in the history of science. So here's the big idea, and it's pretty profound. Instead of trying to calculate every single thing that's happening at infinite energies, which, by the way, we can never actually do, they found a way to mathematically wall off that part of the problem, to just package up their own ignorance. Renormalization is all about neatly separating what we can measure from what we can't. This is the trick right here. So on one hand, the equations start with this theoretical bare value for, say, an electron's mass. That's the part that includes all that chaotic stuff and blows up to infinity. But then renormalization lets you subtract another carefully designed infinity that represents the chaos itself. And what you're left with is the measured value, the nice, finite, real-world number that we actually see in an experiment. And this quote just hits the nail on the head. It's about being honest. They're basically saying, look, we have no idea what's going on at these super tiny, high-energy scales, so instead of pretending, we're just going to bundle up all that chaos, all our ignorance, into a couple of numbers we can actually go out and measure in a lab.
Now, I know this might still sound a little bit like black magic, but it's not magic. There's a method to the madness. It's a recipe, really, for taming infinity and getting answers that actually work.
Okay, so here's how you do it. Step 1, you take your equation that's heading straight for infinity. Step 2, you introduce something called a cutoff. It's basically like telling the math, okay, stop right here before things get out of hand. Step 3, you do the sleight of hand. You wrap up all those messy, almost infinite bits into the numbers you already measured, like the electron's mass. And finally, step 4, you take the cutoff away. And because you've cleverly hidden all the infinities, you're left with a perfect, finite, sensible answer. And, believe it or not, it works. Every single time.
So, all this crazy mathematical trick, was it worth it? Oh, absolutely. The payoff is, well, it's basically the most successful scientific theory we've ever had. Period.
10. Renormalization allows physicists to make predictions that are accurate to over 10 decimal places. To put that in perspective, that's like measuring the distance from New York City to Los Angeles and being accurate to within the width of a single human hair. I mean, that's just insane. The precision is mind-boggling. And it's not just for that one thing either. Renormalization is the mathematical foundation of the standard model of particle physics, our entire rulebook for particles and forces. It gives us the most precise predictions in any field of science. It's used in materials science, and it even helps us understand everyday stuff, like why water freezes into ice. It is, without a doubt, one of the most powerful ideas ever. And this is where we end with this huge lingering question. Is renormalization showing us a deep truth about how reality is built, that the universe itself is layered by scale? Or is it just a really, really clever patch, a mathematical workaround that lets us get the right answers while we wait for the real theory to come along? Physicists are still debating this, which leaves you wondering if our most successful theory is a true window into reality or just the most elegant blindfold we've ever invented.